So in this lecture, I will give a brief introduction to the concept of equilibrium as used in physics. So any object or system of objects can either be in equilibrium or it's not in equilibrium. So let's suppose our object is in equilibrium. What that basically means is that no net force is acting on our object. Our net force along any direction is zero, and that means our object is not accelerating in any direction. So there are two types of equilibrium that we can differentiate whenever we're talking about equilibrium in physics. Static equilibrium as well as dynamic equilibrium. Now let's begin with static equilibrium. Static simply means stationary. So our object is stationary when it's in static equilibrium. And two things must be satisfied for our object to be in static equilibrium. First and foremost, translational as well as rotational velocities must be zero, and secondly, no net force is acting on our object or system of objects. So let's go to the first one. Translational velocity simply means velocity along some axis. So that means our object has no velocity along the x-axis, has no velocity along the y-axis, has no velocity along the z-axis, and in fact has no velocity along any other axis in between. So our object's velocity along any straight line is zero, and that means our object is not accelerating. Its acceleration is in fact zero. Likewise, rotational velocity simply means our object is not moving along any cyclical pathway. So our object is not rotating in any way. And finally, no net force acting on the object in any direction simply means that our object is not accelerating. So its velocity is zero along any direction and its acceleration is zero. Our object is simply stationary. So if all these criteria are satisfied, our object is said to be in static equilibrium. So let's look at a few examples. Suppose we place a book or a box or whatever object on top of some table or some surface. So assuming this object is stationary, as it is in this case, this object is in static equilibrium. And that's because the sum of all the forces along any axis is zero, our object's velocity is zero, and our object is not rotating in any way. For example, if I draw my forces along the y-axis, so the force of gravity is pulling on our object and the force is going upward. Likewise, the normal force that the table or the surface exerts on our box points directly upward. And the sum of these two forces is exactly equal, because according to the third law of motion and the first law of motion, if this object is not zero, then these two forces must have the same magnitude but different directions. So when I sum up these forces, the forces along the y-axis, the forces are zero. Likewise, if I sum up the forces along the x-axis, well, there are no forces along the x-axis. So that means the net force along the x-axis is also zero. Likewise, let's look at this hanging lamp. This hanging lamp is not rotating, it's stationary. And that means likewise, if we take our gravitational force, which is pulling down, and we take our tension in the rope, which is pulling up, these two forces are exactly the same. They have the same magnitude, but different direction. And that means if I sum the forces along the y-axis, I will also get zero. Likewise, since our object is not moving this way, left or right, that means there aren't any forces acting along the x-axis. And that means the sum of the forces along the x-axis are also zero. So put another way, all the forces pointing to the left are exactly the same as all the forces pointing to the right. Likewise, all the forces pointing up is exactly the same as all the forces are pointing down. Now we can also talk about the z direction, but normally we really talk about only two directions on the xy plane, the x direction and the y direction. But note that there's also the z direction and any direction in between the x, y, and z plane. And if our object is in static equilibrium, there's no force in any direction. So in this case, our objects are in station or static equilibrium. So now let's discuss dynamic equilibrium. Now dynamic equilibrium is also an equilibrium, but now it's equilibrium while our object is actually moving. Static means stationary, dynamic means movement. So, in dynamic equilibrium, just like in static equilibrium, the net force on the object is still zero. That means our object is not accelerating according to the first law of motion and second law of motion. But this dynamic equilibrium differs from static equilibrium in the following way. Translational or rotational velocities exist, but these guys are constant. So let me change this to an or, because if one of them is zero but the other one is not zero, our object is still in dynamic equilibrium. So, in other words, in the first case, when we spoke about static equilibrium, our object was stationary. The velocity was zero. Now, our object has some form of velocity, be it rotational or translational, but it's constant. And it's constant because our net force on the object along any axis, along any direction, is exactly zero. And that means, according to the first law of motion, our object will not be accelerating. So our example of dynamic equilibrium is simply a moving object, a car moving at a constant velocity in the same direction. So if the car is moving at a constant velocity with, say, 100 meters per second, that means that our velocity will not change, it will be constant. So our force, net force on the object along any direction is exactly zero. So our dynamic equilibrium, our object is in dynamic equilibrium. Likewise, an object free-falling when it reached its terminal velocity is an object that's undergoing dynamic equilibrium. The force of gravity pulling in our object is exactly the same as the force or the air resistance that's pushing upward, and that's why we have constant velocity. So, we could also have an object or a system of objects that are not in equilibrium. And what this basically means is that the translational or rotational acceleration exists and the velocity is changing. It's not constant. And that's because there is a net force along some axis. And that's exactly why our object begins to accelerate in some direction and our velocity begins to change. So that means we can use our second law of motion to write the following two equations. Now our forces along the x-axis and y-axis are no longer zero. And that means our object of mass m must have some acceleration. And if we're talking about, say, the x-axis, we sum up all the forces along the x-axis, and this equals the mass of the object times its acceleration. Likewise, if we look at the y-axis, the mass of the object times the acceleration equals the sum of all the forces along the y-axis. So, once again, in physics, there are really two types of equilibrium that exist. Static equilibrium as well as dynamic equilibrium. In both cases, our net force along any axis is always zero, and that means our object in both cases will not be accelerating. Its acceleration in both cases is zero. But the difference between static and equilibrium is that static equilibrium means our object is stationary, while dynamic equilibrium means our object is traveling with some constant velocity. So either it's translational or rotational or both velocities are constant. But in both cases, no net force acts on the object. That's why our object is not accelerating. But if the object is not in equilibrium, that means that either translational or rotational or both exist, and these guys are changing. And that's because some net force exists. Some net force exists along some axis, say the x-axis, and this net force creates an acceleration which changes our velocity of the object or system of objects.